So now I'll call this point as some z lambda or something. So z lambda belongs to C1, z lambda belongs to C2. What does that imply? Z lambda belongs to C1 intersection C2 because it belongs to both. That proves the result, right? So it means is a convex set. In fact, I can take any number of intersections, right? A small question to think about. If I take infinite, countable infinite intersection, whether it will be a convex set. Second question, if I take uncountable intersection, so whatever, you should figure out what do you mean by uncountable intersection. You should think whether it will be a convex set or not. So think about this. Okay. Finite, it's clear, right? Induction will tell me that if you give me a billion convex sets and I take intersection, definitely the intersection is a convex set, right? This itself is enough. Okay, now let's use this. Okay, so this, let me introduce you to something. Okay, so called linear. Did I introduce you to linear program? Okay, so what is a linear program? It's something like this. Okay, minimize A transpose X such that maybe I'll use a different C transpose X subject to A1 transpose X less than or equal to B1, A2 transpose X less than or equal to B2, and so on. AN transpose X less than or equal to Bn. There are n constraints. One linear function C transpose X. It's a, what is C transpose X? It's a hyperplane, right? Okay. Now I want to solve this problem. So of course I won't tell you how to solve this problem, but let's try to see what kind of a constraint is this. Well, where do you get these problems? Well, there are so many applications where mainly in computer science where you end up having these kind of constraints. But let's try to understand what these constraints mean. So what is A1 transpose X less than or equal to B1? That means you should collect all those points such that A1 transpose X less than or equal to B1. What does that correspond to? All the half space, right? Everything. What is A2 transpose X less than or equal to B2 correspond to? Right? What does intersection correspond to? Right? A3, A4, maybe like this, right? Not necessarily, but you'll get what? You get some sort of a polygon, right? Well, it's a polygon in n dimension, right? So in 2 dimension it's easy. 3 dimension itself it becomes complicated to imagine, but still you can imagine, right? N dimension you cannot imagine, but it has so many surfaces or faces and they intersect and you have this, right? So this is the constraint set. Now, is the constraint set convex? Yes or no? Why is it convex? Hint is whatever, we just now proved something, right? What is that called? Intersection of convex set is a convex set. So it's intersection of hyperplanes. All the half spaces. All the half spaces are convex, so the intersection is also convex. Okay. Now imagine, okay, in 2 dimension you imagine a polygon. Okay, maybe a pentagon. I have to pick a point in the pentagon that maximizes C transpose X. C transpose X is a plane, right? The height will give you the value of the function. Now, what do you think is the optimal solution? Can you guess? Of course, I won't prove anything mathematically here, but I'll give some intuition. That's all. You imagine a board placed like this and a big pentagon, right, as your constraint. So all the points inside that pentagon. So what do you think is the solution? Yes, any idea? Imagine. Can it be a point somewhere here? Let's argue that out. So can it be a point here? Huh? Yes or no? See, I have some epsilon of room around that point, right? I can still be inside the constraint set, right? The moment you are inside the constraint set, that point is called a feasible point because that's a feasible solution, right? So at least the constraints are met. So now you have some epsilon of room. Can I move in that epsilon of room and increase my objective C transpose X? Is that possible? Obviously, right? I can move in the direction of C, right? C transpose is some vector. I can move in that direction and still get a positive, or if it is minimization, then I'll move in the direction of minus C, right? Do you agree? And still decrease. So this cannot be a point. Same argument applies to any point you pick here, right? Inside. Do you agree? So what do you think is the solution? Where the solution lies? On the surface, right? On the hyperplane, this intersection. Now the second question is, can this point, the solution be on this point here? Can it be a solution? Huh? So now here I can move here or here, right? Two directions. But in general, you'll have more whatever flexibility. But now, given this, do you think this can be a solution? Not really. I can move in this direction or this direction. One of the directions will give me positive inner product with C. So I'll move in that direction, right? So now what happens? Well, these are all, none of these points are solution. Of course, solution should exist, right? So what are the possible points? These points are called extremal points. Okay, only these points can be the solution. Well, which one, you have to figure out, right? So you have to come up with an algorithm. And how many of you have heard of simplex algorithm? Simplex linear program? Huh? Heard of it? Yes or no? Can you raise your hand? Don't worry, I won't ask any question, but have you heard of simplex? Never? Okay, so it's a pretty famous algorithm for finding out solution to linear program. So essentially, simplex, what it does is it's an algorithm to find these corner or the extremal points, which is a solution, right? So that's what people do. Anyway, so this is not my intention was not to show that the extremal points correspond to the solution, but just to give you an intuition about the half spaces, intersection, and so on. It's quite useful, right? Geometrical view. Okay, so now we have intersections, which intersection of convex set is a convex set, and we used some illustration through linear program, and also it introduces you to linear program. Okay, so let's move on. Now let's start looking at what is known as convex functions, right? So what are convex functions? How do you define this? Convex functions. Convex functions look like this, right? So you have something like this, right? This is your convex function. It's downward and it goes down, and then you have one minima here, right? Well, not necessarily one minima. You can also have a bucket kind of a thing, which is also convex. Let's look at what are the properties of this, right? So towards that, let's consider 2 points, right? So one point here. Okay, let me call this as X, right? Maybe I'll call it as X1, and the other point here, okay, X2, right? Now I'll join a line between them, okay, right? I can join a line. So this line is above the function, right? No matter what, you pick this point and draw a line. All this line joining between the 2 points always lie above the function. How do you mathematically write that? So I have to consider a point here, right? For example, I take a point here, right? So the height of this point, right, is always above this point, right, on the function. So for example, this is your function, right? Now the only thing is I have to figure out what this point is, right? What is this point? Convex combination of, so basically it's all the points between, right? It's convex combination of x1 and x2. So how do I write? Right? Fine. What is this point? It's f of that, right? So let me call this as f of lambda x1 plus 1 minus lambda x2. This is the height. Now comes the question. So what is this point, this height? What is this height? Huh? See, I'm taking this height, and it's a linear convex combination of the heights, right? So this is nothing but lambda f of x1. See, height of this is f of x1, right? So this is f of x1. This is f of x2. So it's convex combination of f of x1 and f of x2, right? That gives me this point, right? This is fine. Okay. Now what is convexity? This height is more than f of lambda, whatever, right? So this clearly says f of lambda x1 plus 1 minus lambda x2 is smaller than or equal to f of lambda times f of x1 plus 1 minus lambda times f of x2. Well, this should be true for any x1, x2 that you pick in the domain of the function and any lambda between 0 and 1, right? So that is the definition of a convex function. Shall we write the definition now? So intuition is clear, right? So we can write the definition. So definition, we'll write a general definition, okay? So we say that f, which is mapping from Rn to R, is a convex function if you take any 2 points in the domain. So for every x1, x2, okay, I'm going to use a notation now, okay? So I'm going to use the domain of f. That means all those points over which f is defined, okay? If I want to basically not, I mean, I have to avoid this, what should I do? I'll redefine my function in such a way that my new function is equal to the old function in the domain. Otherwise, it's infinity. Okay, I can do a lot of such things, but right now I'll write it as is. Okay, domain of the function lambda belonging to 0, 1 for any x1, x2, and for any lambda belonging to this, f of lambda x1 plus 1 minus lambda x2 is less than or equal to lambda f of x1 plus 1 minus lambda f of x2. Right? This is the definition of, this is how you convert geometry into Greek and Latin, right? Called math. Okay, so we have this definition. Let's look at some of the consequences of this definition. Okay, so what are the consequences? Okay, so let's say, what does it imply? Consequences are, yeah. Okay, so what I'm going to do is you take a function to R. You have this function be convex. So I'm taking a convex function to begin with. Think of always convex function will be like this. Okay. Now we take 2 points. Okay, so let's say let xy belong to domain of f. We take 2 points x and y. Okay. I'll take convex combination of these 2 points. One way of writing that is lambda x plus 1 minus lambda y, right? Or I can write it as y plus 1 minus lambda x, right? You agree? Lambda x plus 1 minus lambda y, or x plus, or y plus 1 minus lambda x. Do you agree with that? So f of, I'll take this, okay, I'll write it as is. This is the convex combination, right? But what is this? This will be y plus, sorry, this is f of y plus, because y gets multiplied by 1, you get y plus lambda times x minus y. Do you agree with this? Right? By convexity, what do we have? This is less than or equal to lambda times f of x plus 1 minus lambda times f of y, right? You agree with this?